truth has underpinned the entire digital universe. The creation of the most powerful microchips on Earth is an act of industrial alchemy, an art perfected by a single entity, requiring colossal machines that devour energy on an almost unimaginable scale. This EUV lithography monopoly by ASML of the Netherlands has been the silicon gatekeeper, controlling the very flow of advanced technology to every corner of the globe. But what if the gates are about to swing wide open, forced by a secret, leaked blueprint that suggests a future where the rules of power are fundamentally rewritten? Revenau stands at the precipice of revealing a development so monumental, so disruptive, that it could fundamentally re-engineer the very landscape of the global chip war. Reports, initially whispered in the shadows of the semiconductor industry, are now solidifying around a shocking claim. China has purportedly developed an EUV blueprint capable of manufacturing next-generation chips with a staggering 90% less power than ASML's current energy-intensive systems. This isn't just a cost-saving measure, it's a potential energy revolution at the nanoscale, threatening to dissolve Western technological chokeholds and reshape the geopolitical power balance. This is not merely an alternative. It is a declaration of technological independence that the world was not prepared for. To fully appreciate the seismic impact of this leak, we must first dissect the current titan, ASML's laser-produced plasma, LPP, EUV lithography. This method, while a triumph of engineering, is an undisputed energy behemoth. The core principle involves firing two powerful lasers, a pre-pulse and a main pulse, at microscopic droplets of molten tin, each smaller than a human hair, as they freefall through a vacuum chamber. This vaporizes the tin, creating a superheated plasma that then emits the crucial 13.5 nanometer EUV light. The challenges are immense. Extreme energy conversion, only a tiny fraction, around 0.1% or less, of the laser energy converts into usable EUV light. The rest is dissipated as heat, requiring elaborate cooling systems that further consume power. Debris management. The vaporization process creates tin debris, which must be precisely managed to prevent damage to the incredibly expensive and sensitive multi-layer mirrors. This necessitates sophisticated vacuum systems and debris mitigation, all of which add to the energy overhead. High repetition rates. To achieve the necessary throughput, wafers per hour, the lasers must fire thousands, even tens of thousands of pulses per second. This sustained, high-power operation translates to an immense electrical demand for an entire fab. A single ASML EUV machine, operating at full capacity, can consume power equivalent to a small town. When you consider the numerous machines in a leading-edge semiconductor fab, the energy footprint is staggering. This isn't just an operational cost. It contributes significantly to the carbon footprint of the digital economy and places tangible strain on national power grids. The pursuit of smaller, more powerful chips has inadvertently created an energy-intensive industrial leviathan, making existing LPP technology a paradox of efficiency, incredibly precise, yet incredibly wasteful in its energy conversion. This reliance on high-power LPP has created a natural barrier to entry, limiting advanced chip manufacturing to nations with robust, stable, and often carbon-heavy energy infrastructures. Now, enter the supposed Chinese breakthrough, laser-induced discharge plasma, or LDP. While both LPP and LDP aim for the same precise 13.5 nanometers EUV wavelength, their fundamental energy application is radically different. Instead of relying almost solely on high-power lasers for both tin vaporization and plasma excitation, LDP employs a two-stage approach that leverages electrical discharge. Here's the alleged genius: pre-pulse laser. A much lower-power laser initiates a small, controlled plasma plume from the tin target. This initial ionization requires significantly less energy than ASML's brute-force vaporization. Electrical discharge. Main pulse. Crucially, a powerful electrical discharge is then introduced between two electrodes through this preformed plasma plume. This precisely controlled electrical current rapidly heats and excites the tin plasma to the extreme temperatures necessary to generate EUV light. This process, by converting electrical energy directly into plasma excitation, is inherently more efficient than relying on a series of energy conversions from laser light to heat to plasma. The claims of 90% less power consumption stem from this fundamental shift in energy input. The LDP system avoids the massive energy losses associated with generating and transmitting the extremely high-power laser pulses required for LPP. This could mean reduced heat management. Less power consumed means less waste heat generated, simplifying cooling systems and potentially reducing component wear. Simpler source architecture. Fewer high-power laser modules translate to a potentially less complex, more compact, and easier to maintain EUV source. This could lower both the manufacturing cost of the machine itself and its footprint within a fab. Improved conversion efficiency. The direct electrical excitation might lead to a higher conversion efficiency of input energy to useful EUV light, a critical metric in lithography. If these verified facts from the leaked blueprint hold true at commercial scale, the implications for semiconductor manufacturing are not just evolutionary, but potentially revolutionary. This would be a genuine technological achievement that directly counters ASML's long-held advantages in energy efficiency and complexity. This shift in EUV lithography, moving from LPP to the potentially far more efficient LDP, could trigger a global shift of unprecedented scale. If you're finding this deep dive into China's tech breakthroughs as vital as we are, and you want to support independent analysis that cuts through the noise, please hit that like button right now. Seriously, it helps us immensely. Don't keep this crucial information to yourself. Share this video with your networks, your friends, anyone who needs to understand the real forces reshaping our world. And if you haven't already, subscribe to the Revo Now channel and activate that notification bell so you're always ahead of the curve on the biggest tech stories and geopolitical developments. Your engagement makes this research possible. The geopolitical ramifications of this alleged EUV blueprint leak extend far beyond simple trade sanctions. For years, the United States, in concert with its allies like the Netherlands, Japan, and South Korea, has strategically utilized export controls on advanced semiconductor equipment to slow China's progress in leading-edge chip manufacturing. The ASML monopoly was a key strategic choke point, a lever to control China's access to the most sophisticated computing power essential for AI development, quantum computing research, and advanced military applications. If China successfully deploys LDP-based EUV at commercial scale, it effectively sidesteps this critical bottleneck. This isn't just about making their own chips, it's about achieving genuine technological sovereignty. Reduced leverage. The West's ability to exert pressure through tech export controls would significantly diminish. New supply chains. It could spur the creation of entirely new, independent supply chains for advanced chips, potentially leading to a more bifurcated global tech ecosystem. Redefined alliances. Nations previously reliant on Western tech could explore new collaborations, particularly with China, if the LDP method proves to be more accessible or cost-effective. Accelerated domestic innovation. Freed from external constraints, China could further accelerate its indigenous semiconductor research and development, potentially leading to unforeseen breakthroughs in other areas. This scenario represents a fundamental shift in the global balance of power, moving beyond simple economic competition to a more complex struggle for technological self-determination. The implications for global stability and future technological supremacy are immense. While the LDP blueprint is a monumental scientific achievement, the journey from a leaked design to a high-volume, commercially viable EUV fab is still fraught with immense challenges. The semiconductor ecosystem is not just about the EUV source. It's a vast, intricate web of specialized technologies. Ultra-precision optics. Manufacturing the multilayer mirrors that guide EUV light requires astronomical precision. Literally atom-by-atom control. Even if the LDP source is simpler, the optics remain incredibly demanding. Photoresists and chemicals. Developing and consistently manufacturing ultra-sensitive photoresists that accurately capture the EUV pattern on silicon wafers is a field of its own, requiring deep chemical expertise. Metrology and inspection. After lithography, the etched patterns must be precisely measured and inspected for defects. This requires incredibly advanced metrology tools that detect flaws at the nanometer scale. Mask technology. The masks or reticles that contain the circuit patterns are themselves ultra-complex, defect-free, and incredibly expensive components. Software and automation. Running an advanced fab requires sophisticated software for process control, yield management, and automation, integrating hundreds of different machines. Talent pool. Perhaps the greatest challenge is assembling and nurturing a deep pool of highly specialized engineers, physicists, chemists, and materials scientists with decades of collective experience. ASML's current dominance is built on decades of incremental improvements and a global supply chain of hundreds of highly specialized companies. China, despite massive investments, is still playing catch-up in many of these critical ancillary technologies. The key questions facing the LDP blueprint are, can China achieve the extremely high yield rates and throughput, wafers per hour, necessary for profitable mass production? Can they ensure the long-term reliability and stability of these complex machines under continuous operation? These are multi-billion-dollar questions, requiring sustained effort for years, if not decades. The leak of this EUV blueprint, hinting at 90% less power consumption from an LDP approach compared to ASML's LPP, is a powerful signal of China's relentless pursuit of technological independence. While the ultimate outcome remains to be seen, this development has undeniably injected a fresh wave of urgency and uncertainty into the global semiconductor industry. Riva now is here to unravel the engineering marvel that has sent shockwaves through the entire semiconductor industry. Prepare for the revelation that SMIC, China's leading foundry, has reportedly achieved the once unthinkable 5 nanometers chip development using DUV lithography. This is not a drill. This is not speculation. This is a verified achievement that defies the conventional wisdom of chip manufacturing. Think about the scale of this feat: overcoming immense technological barriers, bypassing critical export controls, and literally forging a new path in the most complex industry on Earth. The implications for global technology, geopolitical power, and the very definition of innovation are nothing short of monumental. We're talking about a game-changing moment that demands your full attention, now. To truly grasp the magnitude of SMIC's 5 nanometers achievement with DUV, we need a quick dive into the arcane world of chip manufacturing, specifically lithography. Imagine trying to paint an incredibly detailed mural, not with a fine brush, but with a roller. That's a simplified analogy for the challenge here. At the heart of making microchips are complex processes that essentially print microscopic circuits onto silicon wafers. This printing is done using light. DUV, deep ultraviolet lithography, uses light with a wavelength of 193 nanometers. For years, this was the industry standard. It's fantastic for manufacturing chips down to about 7 nanometers, but going much smaller than that becomes incredibly difficult. Think of trying to draw a line thinner than your pen tip. You can try, but it gets blurry and imprecise. EUV, extreme ultraviolet, lithography uses a much shorter wavelength, just 13.5 nanometers. This tiny wavelength allows for far more precise, incredibly fine lines and patterns. It's the fine brush that enables companies like TSMC and Samsung to mass-produce chips at 7 nanometers, 5 nanometers, 3 nanometers, and even smaller nodes, pushing the boundaries of Moore's law. The consensus in the semiconductor industry was absolute. To get to 5 nanometers, to cram billions of transistors onto a chip the size of a fingernail, EUV machines were indispensable. These machines are not just expensive, they are incredibly complex, require a global supply chain of highly specialized components, and are controlled by a single company, ASML, based in the Netherlands. Due to export controls and geopolitical tensions, China has effectively been cut off from acquiring these critical EUV tools. So, for SMIC to achieve 5 nanometers development with DUV means they've found a way to draw ultrafine lines with a blunter instrument. This involves highly sophisticated multi-patterning techniques, where layers are printed, etched, and printed again with incredible precision. It's exponentially more complex, costly, and difficult to achieve high yields. The fact that SMIC has reportedly pulled this off is nothing short of an engineering miracle, and it fundamentally changes the strategic calculus of the global chip industry. This isn't an overnight fluke. It's the culmination of years of relentless effort, massive investment, and a determined national strategy for chip independence. SMIC, as China's leading foundry, has been at the forefront of this push. Remember the surprise from late 2023 when Huawei released their Mate 60 Pro smartphone, powered by the domestically produced Kirin 9000's chip? That 7 nanometers chip, produced by SMIC using DUV, already shocked the world. It signaled that China was far more resilient and capable than many believed, especially given the strict US export controls on advanced semiconductor technology. Now, reports indicate that SMIC have started production of its 5 nanometer chip in 2025. This suggests they've refined their multi-patterning techniques, perhaps optimized their equipment, and innovated in ways thought impossible with DUV. This isn't about perfectly matching the yield or cost efficiency of EUV-produced chips from global leaders like TSMC or Samsung, at least not yet. It's about demonstrating the sheer capability to overcome seemingly insurmountable technological barriers and achieve a level of process technology that ensures China's critical industries from AI to 5G can continue to advance with domestically produced components. Huawei, a key partner, is reportedly using these advanced domestic chips in their latest Mate 70 and Pura 80 series smartphones. There are even discussions about Huawei actively developing its own EDA, electronic design automation chip-making tools. These are the crucial software tools required to design and optimize chips. If China achieves significant breakthroughs in EDA, it removes yet another critical dependency, further solidifying its chip independence and accelerating its progress in chip fabrication. This symbiotic relationship between Huawei's chip design and SMIC's manufacturing prowess is a formidable force. The semiconductor industry is the bedrock of our modern world, and what SMIC has reportedly achieved is a genuine game-changer. If you're as fascinated by this technological breakthrough and its global implications as we are, and you believe in deep, unbiased analysis that cuts through the noise, please take a moment right now, smash that like button. It truly fuels our investigations and helps us uncover more vital stories like this. Share this video with everyone you know who needs to understand this monumental chip innovation. And if you haven't already, subscribe to the Revo Now channel and hit that notification bell so you never miss our urgent updates and groundbreaking exposés into the true forces shaping our technological future. Your support makes this work possible, and your engagement builds our community of informed viewers. SMIC's 5 nanometers achievement isn't happening in a vacuum. It's part of a much larger, incredibly ambitious push to build a complete, self-sufficient chip ecosystem within China. This includes massive advancements in other critical areas. Memory breakthroughs. China's memory chip manufacturers are also making significant strides. Yangtze Memory Technologies Corporation, YMTC, and Changshin Memory Technologies, CXMT, are leading this charge. Tech Insights, a respected industry analysis firm, has confirmed the market availability of YMTC's new and advanced X-Tacking 4 X2YYYL1 TB3D TLC NAND chip. This is highly competitive in the NAND flash market, crucial for data storage in everything from smartphones to data centers. Similarly, CXMT is showing substantial progress with its G4 DDR5 DRAM, which is essential for computer memory. While they still trail global giants like Samsung and SK Hynix, their consistent material innovation and increasing production capacity are undeniable achievements despite equipment limitations. Massive investment. China continues to pour astronomical sums into its semiconductor sector. Cities like Shenzhen are establishing multi-billion yuan investment funds specifically to bolster their integrated circuit industries. Companies like Xiaomi have publicly committed to decade-long multi-billion-dollar spending programs for semiconductor development, with significant funds already invested in cutting-edge chips like their 3 nanometers X-Ring 01. This relentless flow of capital is crucial for building new fabs, fabrication plants, and scaling up production. Infrastructure expansion. The Chinese mainland is expected to remain the largest market for new semiconductor equipment in 2025. This isn't just about advanced nodes, it also includes robust investment in mature process nodes, which are vital for a vast array of essential components in industries like automotive, consumer electronics, and industrial control systems. This ensures a broad base of domestic chip production. Furthermore, Huawei is reportedly constructing a mega chip facility in Shenzhen, specifically for manufacturing its own Kirin and Ascend AI chips, solidifying its strategic vertical integration and bolstering national chip self-sufficiency. This holistic approach, targeting every segment of the semiconductor supply chain, is designed to insulate China from external pressures and secure its technological future. The SMIC 5 nanometers breakthrough fundamentally alters the landscape of the global chip war. For years, US export controls on advanced chip-making equipment and materials were seen as the primary lever to slow China's technological ascent, particularly in areas with military applications like AI and advanced computing. The assumption was that without EUV, cutting-edge production would remain out of reach. But SMIC's achievement challenges that assumption directly. It demonstrates China's remarkable resilience and its unwavering determination to achieve technological independence, even in the face of immense pressure. This isn't just an economic story, it's a profound geopolitical development. Rethinking sanctions. This breakthrough forces a re-evaluation of the effectiveness of current export control strategies. While restrictions undoubtedly make China's progress harder and more costly, they haven't halted it. This could lead to new policy debates and potentially even more stringent measures from the US and its allies. National security implications. For nations relying on a few key global chip foundries, China's increasing self-reliance in semiconductors has significant national security implications. It introduces a new variable into strategic planning and reduces vulnerability to external supply chain disruptions. Global competition intensifies. The chip industry is now more competitive than ever. China's ability to produce advanced chips domestically will intensify the race for technological leadership, particularly in next-generation AI, 5G infrastructure, and autonomous vehicle technologies, where chip performance is paramount. Redrawing the tech map. This development signifies a potential reshaping of the global technology map, with more diversified centers of advanced chip production. It highlights the growing importance of domestic innovation and strategic investment in critical technologies for all major economies. The impossible becoming possible means the chip war is far from over. It's simply evolving, and the stakes have just gotten even higher. The SMIC 5 nanometers achievement with DUV is an incredible testament to human ingenuity and national determination. It fundamentally shifts the narrative around China's semiconductor capabilities. What does this unprecedented breakthrough mean for the future of global technology in your opinion? How will this impact the devices you use, the economy you live in, and the balance of world power? Share your insights, your questions, and your thoughts on this astonishing development in the comments below. Your perspective is invaluable as we navigate this complex new chip landscape, and as we continue to cut through the noise and reveal the true forces reshaping our technological future. What other hidden innovations, emerging technologies, or geopolitical shifts do you want RevoNow to investigate next? Your questions drive our next deep dive into the unfolding reality of our world. Thank you for joining us on this critical journey. Stay informed, stay ahead. This is RevoNow signing off.
Subscribe to Revo now and join our vibrant community of forward thinkers, change makers, and revolutionaries.